piezoelectricity. I think some of the items I can do very quickly. I want to try to see what is piezoelectricity in terms of a very simple model. So if you imagine that you have ions that are positive and negative, positive, negative, positive, so a simple structure. And then you have two types of springs. So one is softer, one is harder, yeah, and arranged in this systematic way. So this can be looked upon as a unit cell if you want, yeah. And you see that this is a polar axis, yeah, because when you turn it upside down, it's different, yeah. So this is a polar structure. And then you can calculate when you apply an electric field. Of course, the negative ones are going in one direction, the positive in the other direction. And since one spring is weaker than the other one, so one direction is more squeezed than the other. And for this reason, the one type of ions is displaced more than the other type of ions, or the center of gravity is differently coming out differently. And you can then calculate the strain. In one section, it's this one. It's the force divided by the spring constant of one spring, and here is minus the force because it's a negative charge divided by the other spring constant. You make the difference or the sum of both. They are not, since they are, you see, since the spring constants are not equal, the sum comes out different from zero, and you can then get the strain or something like that. You see that it must be also related to the distance, because this is yeah, that's a distance, and here is the charge. So this comes out directly like this. So you can conclude, yeah, well, I need a crystal where I have two spring constants that are different. Yeah, it must be polar, and the charges must be as high as possible. Yeah, and the distance must be as short as possible. Yeah, if you look at this, well, practically ionic crystals are a solution. Yeah, so that's why it's, ionic crystals are very good, because A is short, and yeah, so this large Q, small a, and long, and yeah. You can look in your structures where is the small spring constant, where is the spring constant. Yeah. The direct effect works the same way. I mean, you will find out that exactly this gives the same formula. And that's also good that it gives the same formula, because they should be the same. So, this here is the, you know, you have red and blue on top of each other, then you pull, and then you get the charges out. Yeah? But one side is red, the other is blue, because they, because of these chains. Yeah, because this is the charge separation. And when you think, well, what happens in 2 and 3 dimensions, and you try to arrange these springs to get charge compensation, yeah, so you have always positive and negative close to each other. Otherwise, you get an unbalanced charge compensation. And you see that the two ends must be different. So crystals then have some kind of positive or negative faces. And for instance, in aluminum nitride, one speaks about the N-polar surface or aluminium polar surface. So they are different. And it's not only dipole, in the dipole sense different. You see it's dipolar surface. Also chemically they are different. So when you find always in such structures agents that attack one polarity but not the other. It's very interesting. So this means that, for instance, ferroelectric materials can also be used in electrochemical reactions in an interesting way. So it has also been shown. So that's, and this is the story with missing inversion center. You know already. I mean, that's a visualization in 3D. This is a hexagon. But every second corner has a different charge. You pull, and then you see, well, afterwards, pulling it's polar, but not before. So you create a polarization by applying a force or by pulling, yeah. And so this is. In thin films, it's like this, that this pure, how to say, materials like quartz, we cannot use. Yeah? Some people try to grow quartz that is, how to say, oriented. So some French group, in fact, managed to do that, but only little grains. So now to have all the grains in the right orientation, completely difficult. I think this will be not managed. It's very, very difficult. So that's why we always stick to polar structures in thin films, because we have some means to grow not only oriented that the z-axis is up, for instance, but also that the plus c or minus c is oriented. So this has to be done. In Piezoelectric, no problem because it switches the electric field, but this is an issue of growth, how to do that. In airline, we can do that thanks to plasma impact, in fact. Well, yeah, so we have seen these two types of these polar axis systems. So there first is quartz type system. We cannot do in thin films, but number two we can do in thin films. And this is a sketch of the aluminum nitride structure. So you have tetrahedrons. Let's say this is a nitrogen tetrahedron. In the center is an aluminium ion making a tetrahedron in the other direction. Yeah? And you see it's polar. When you turn it upside down, it's different. Yeah? You invert the charges, so it's not possible. Yeah, so these are these two possibilities. Yeah, I think we know already. Now, you are learned also about the strain. Yeah, what is strain? So it's this, how do you say, definition of the derivatives of the displacement in I direction towards the in direction of j, and the other way around. It's symmetric, so it's always symmetric. And you can define it in symmetrized way so that you don't have rotation. Yeah? So this is, you see, that's a shear here. That's the symmetric way. This is the strain. The asymmetric way is rotation. But by the way, also the translation goes away. Yeah? Translation instead. So it's something that has no rotation, no translation. Just that's the, yeah, you have already learned that as well. What the stress is. Maybe the shear stress is a little specific, yeah. So you have the the forces in the plane. And then many of you know these old formulas where you have one Poisson ratio and so on, yeah. And one E module. So this is the isotropic material, yeah. And so this looks very simple. And many people work with this, although they deal with crystals, and sometimes we should really say, well, now you put S13 and not Poisson ratio, because it makes things more clear. Yeah? So, what is special with isotropic materials is that the shear modulus, it depends on the Young's modulus. Yeah? It's not independent. That's typical for isotropic materials. Yeah? Because when you make a cubic structure like silicon, they are not, they are independent, so they have different values. So that's specific. Hooke's law, stiffness, compliance, you heard about that. Then also you heard about engineering notation. Yeah, maybe to add about specific for the piezoelectric tensor. We write in this way the same tensor in direct and converse mode. And the problem is you realize you have to know which index is for the electric field and which stands for strain or stress. Yeah. So the convention is in fact that we use the notation like in the direct effect and write it in the same way also in the converse effect. It's E. Huh? It's in fact it should be the transposed matrix, but it is not. Huh? So that's just to be sure. This is the stiffness. You know this I write for our students. You heard that it is a symmetric matrix. So this side here is the same as this side. And then you can calculate there must be 21, maximum 21 coefficients. You know. You're asking about symmetry. Yeah? You see, symmetry saves us a lot of work. Yeah? Because if you use no symmetry, you use tremendously the number of independent coefficients. Simple argumentation from 81 to 21. Simple knowledge. And then you go to a cube from 21 to 3. Yeah, so this is now this 3 Piezoelectric coefficients. So you have this longitudinal one. Yeah, notice what happens. So it's usually like this. Along the polar axis, you get an elongation, and perpendicularly you get a shrinkage. So this is T31 is negative, T33 is positive, and the other one here is the response. That's the shear. Yeah. So yes. So that's T15 E1. Yeah. Yeah. Now. Then there's also a very interesting concept, you know. You can everything write in matrices. So this is what we call the constitutive equation. So we have, now I went to a simple model. With, you can imagine this as tensors or as coefficients of a simple model. The strain is equal to the compliance times the stress plus dE. And there is the compliance defined at constant E, because you know when E is 0, it's for a 0 E field. So this must be compatible with the choice of your variables. TE variable system, meaning both are intensive variables. The stress is intensive, it's a local property, and the electric field is intensive. It doesn't give you a size effect. Yeah? The others are called extensive variables when it's proportional to the volume, to the number of particles, or and so on. So the strain, in fact, is extensive because it's related to the, even though you divide by the total dimension, but it's considered to be like volume, and the D field also is like volume, is like a size effect because it's the number of charges. Although you divide by the area, and it's a tensor charge, but this gives you, let's say, a size description. That's why. And in my equation, you have this. So you have these variables, or this matrix times this matrix. And then you have the coupling constant. And the coupling constant in such system, it's like in quantum mechanics. Yeah, you know also that it's always the square of the diagonal elements here over the product of the. Sorry, the square of the off-diagonal element over the product of the diagonal element. So this is the coupling constant. Epsilon T.
Yeah. Just on the top is epsilon T, and in the matrix epsilon S.
That's on the wrong side here. Sorry. Yeah, that has to do with it. No, epsilon 0 is not. I don't know. Oh yeah, sorry, that's a mistake. Yeah, right. Sorry. Yeah. That's a mistake. Terrible mistake. This should be T, yeah? Like here, it's T. Yeah. Yeah, of course. No, this is a terrible mistake. I have to correct it. Yeah, thank you. Yeah. Exactly, this is the coupling coefficient, and you can also make the simple calculation. You take the ratio of the mechanical energy you produce divided by the electrical energy you apply. So the strain is, this is 1/2 times the compliance times the strain squared. When we have a polycrystalline material, also it's possible, of course, that not all grains have the same orientation, or we have domains with grains that have not the same polarization, or domains with different polarizations, directions. And of course, it's clear when you have, for instance, situation polarization down here, polarization up, like here, you get effects that are opposite in the sign. And if you have a mixture of this, then you may have zero effect. As said, in this direction is 0. You may have a shear deformation, but not an step. And in general, you can write it like this. So it's quite a formula you can calculate. So it's since we deal with a second rank tensor, we have always this sinus square and cosine square and so on. Yeah? So you simply have to write S in the right term and Z in the right term and get them this. So that is complicated. Then would like to speak about the thin film and the substrate. So what we have very frequently is this situation that we have a thin film on a substrate. And the substrate is elastic. So it's an elastic body. For instance, we have a membrane, or we have a cantilever, we have a bridge. The substrate is of about the same thickness, not much more thick than the film. And so the question is, how is this behaving? Yeah? To describe it. So under usual operation conditions, in fact, yeah, we have no stress. So most of the time, we do not apply a vertical stress outside to push on the film. Your membrane would be destroyed or something like that. It's an effect when you, for instance, consider inertial structures where you have, for instance, a bridge and a mass on top of this bridge, and you vibrate it, then of course the stress would work. But many times we just have here atmospheric pressure and nothing more. Yeah? Then about the strain, we know that the strain must be continuous. I mean, I don't speak about the intrinsic strain of materials, which can be, of course, different on both sides. Yeah? Because you can make them with different stresses. But with the piezoelectric strain, I mean the strain change, yeah? The strain change. So when I'm speaking here about strain, it's always the strain change due to the piezoelectric effect, for instance. So this must be continuous. This is the only thing what we know of this interface, yeah? It must be continuous, because otherwise you have delamination. If the strain would be different, the strain change, then you have a delamination, yeah? So they must move together, yeah? Otherwise fly away, yeah? So in the direct effect, what is of interest is the strain that is applied to the film, because we can, since it's that have to go together with the substrate, we know something about the strain in this plane. We don't know anything about the stress, yeah? Normally, yeah? So in fact, it's, let's say, the natural variable to describe something in this direct effect. And in the converse effect, in fact, when we apply an electric field, we create this in-plane stress. The stress here is sigma, in-plane stress. And this stress will make a bending moment with respect to this elastic body that is below. So with respect to the neutral plane. The neutral plane is there where they have no length change. There is no length change. So for instance, if it's tensile, it would make such a deformation. So there would be a compression on top of the neutral plane and a dilatation below that. Yeah. So this is the definition of this one. And there will be also a strain made by the piezoelectric effect. So in this case, we can speak about the strain in the third direction. And so to compare here with the bulk. So in the bulk, of course, we don't make such condensation here. Everything is the piezoelectric body. And with two electrodes, we very conveniently take, in fact, the stress as variables, because we know what we apply from outside. Yeah? The stress is a very convenient parameter. Yeah? It's more easy to understand what one is doing with stress. So we say, okay, either the stress is free, so then we have these t coefficients that are valid, and we can describe it in this way. Yeah? That's a direct effect. Now in the thin film, it's convenient to describe it as strain in the plane, because the strain has to do with the deformation of the whole structure, and so we describe it in this way. But the stress out of plane, because most of the time is zero, so we know the stress out of plane. And what is then funny, we can say, well, we get a kind of renormalization, assuming that we separate. So we can write it this way, that we have D3 is dielectric constant, which is then also different because of this let's say, situation of the thin film. So you get a different dielectric constant, what you measure in a thin film. It's not simply epsilon 33 at constant stress, for instance, but it's that one. Huh? It's a little bit less, so it goes in direction of epsilon s. Yeah? But it's in between epsilon 33 t and epsilon 33 s. Then you have this transverse coefficient, which can be written in this way, which I call this E31F here. And you have this renormalized D33 coefficient